Okay, so I will be talking about the Polaronic Eigenstates in 2D Perovskites. Okay, so some background is a perovskite is a mineral composed of calcium titanate or other compounds with similar crystal structures. And this is the calcium titanate pictured. Understanding these electronic properties is crucial for tailoring their characteristics and optimizing charge transfer and also designing efficient devices. These address the stability challenges and enables the harnessing of the quantum confinement effects. So polarons and eigenstates. So polaron, kind of building off of what Kaiden said, is a quasi-particle which results from an interaction between an electron and a lattice structure of a solid. This leads to localized distortion and collective behavior. The Polaronic eigenstates are the quantum states of a system that incorporates the effects of electron-photon interactions, and this is what leads to the formation of the polarons. So this is the main equation that was used from the MATLAB that made the code go, and there's two different parts of this. So on the left is for Polaronic cases, and on the right is for non-Polaronic cases. And the only real difference is taking it to either Polaron or taking it to non-Polaron. Okay, and then this image kind of shows between a Polaronic state and then the non-Polaronic. So this would be the Polaronic, and we can see in the conduction band, there's a lot of electrons up there because they're so close. No, so they're so loose around the nucleus, and then there's none in the valence band or the insulator. It's empty. And then for image B, that kind of just shows the crystal structure. And
valence is filled, conduction is empty.
yes.
Right, okay, good.
And the crystal structure and just how it's similar throughout the whole structure. Okay, so some of the results, this is looking specifically at the first eigenstate for the Polaronic state. As you can see, there's a really big concentration in the top corner. And that just shows that's where all the ions are, and the electrons are attracted to the ions because of their charge. So they're all closely grouped in that one corner. And you can kind of see it through all three images. Okay, this is a video for the Polaronic eigenstates. It's through 1 through 20. Kind of seeing them move. Okay. This is the non-Polaronic 1 through 20. Okay, so kind of comparing the non-Polaron and Polaron with some screenshots from the two previous videos. So the top is the non-Polaron and the bottom is the Polaron. And I took just a few of the states to specifically look at. So the first one, you can see the biggest difference where the non-Polaron doesn't have any big concentration and it's just like a lattice or grid pattern. While the Polaron has a very big concentration in one corner because of the charges. And as you can see, as it goes up in eigenstate, they look more similar to one another until like 18 and then like 19 and 20, you can't really tell which one is the non-Polaron and Polaron without labeling it because they look so similar. Okay, so in conclusion, this shows that like the relationship between the Polaron and the non-Polaron can be shown with the MATLAB code. It also shows that as the eigenlevel increases, that the difference between polarons and non-polarons are harder to distinguish. And some more challenges with this field of study is that it takes very advanced theoretical models to describe the interactions between these electrons and lattice vibrations.